Okay, let me look at this question here. I think I remember as I was programming in this question, kind of thinking, it's challenging. Yeah. But there's a hint and everything, so let's work through it. Um, so it's question 104 from chapter 11. Again, it's end of the chapter questions. It's like either additional or challenge questions. It says a particle's path, so incoming particle is bent when it passes through a region of non-zero magnetic field, although its speed remains unchanged. This is very useful for beam steering and it's just background information that you could forget. That doesn't affect your question, that is the background. I think consider a proton of some speed. This is that's pretty slow. I guess that's non-relativistic. Definitely, it's like a factor of 100 or so smaller than speed of light. Entering a region of uniform magnetic field let me just make sure the direction is right. So if V is that way, cross V cross, V cross B. For protons, the force will be upward. So the path bending this way makes sense to me. Over a 5 centimeter region, magnetic field is perpendicular to velocity. By how much angle will the path of the proton be bent? Into the particle comes out tangent to a circle and use. Okay. So tangent to a circle, I think it's referring to this. So I can imagine kind of connecting the dots for the portion of the path that they didn't draw. Like this path, as it enters the magnetic field region, it's going to start to bend, and it'll start to bend in this way. And basically, you imagine kind of an arc of a circle. I can't draw. Let me actually draw it this way. I think this might actually be better. So you can imagine a cord that connects this point to that point. That's just a straight line. And the arc of the circle that has this starting and ending point, it'll basically look like this. It'll be very close to that cord. But this arc, the way I guess it's supposed to be, is that the direction this is going, that should actually be the same as the direction this velocity is going. My drawing is just not very good. So that's I think the part of the hint talking about the particle comes out tangent to a circle. And what does it mean? Use the small angle approximation. I think this question has a hint. Let's look at it. It kind of tells you how to work out the geometry. It says start by figuring out the radius of the circular path of the proton inside the unit. Okay, I can do that. So the chord, so that would be this L here. That's the L. And it's giving me this relationship. It's related to the angle of deflection. So the this theta, angle of deflection by L is equal to 2r sine theta. And I don't think that's shown here, but with some auxiliary figures, I think you can figure it out. Imagine you have like this arc is part of a circle. So this is my radius r, or lowercase r is what the hint is using. So let me use that. R, then I think this is the geometry that I'm supposed to imagine. This is an isosceles triangle because of the two r's being the same. To drop down a perpendicular bisector to have a right triangle on each side. Then this portion will be L over 2, and that's related to this R. And I think the part that I'm supposed to prove is that this theta, that should be the same as I think this entire theta. How do I prove that? I guess the way to prove it would be, so again, my drawing is terrible, but I have this right angle here, and on this side, the radius and the path, that should also still be right angle. So so this vector, turned by theta degrees to get to this point. So you imagine kind of turning this entire thing by theta. That's what gives you the theta central angle there. So with all that, so here I think I can use sine of the angle. So this is half of the angle. Sine of theta over 2 is equal to the opposite, L over 2 divided by R. Then solving for L, the 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 chord for the circular arc. The L is equal to both the 2 and r on the numerator now. 2 times r sine of theta over 2. Yeah, that's the relationship that they gave us in the hint. I'm just kind of explaining where that comes from. Use a small angle approximation to simplify the expression for theta in terms of magnetic field region width. Oh, okay. Width and okay. I guess I'll write out the rest. So the path of the proton is bent by that. So start by figuring out, right? So I need to do the dynamics analysis to get that radius of the circular path. So for the particle that was originally moving that way, v, I'm given the speed, right? Yeah, v naught. It's a proton. I have the mass of the proton, or I can look it up. And in a region with a magnetic field pointing into the screen, then v cross, right? V cross b. Yeah, v cross b into the screen. So force is upward. So I have an upward magnetic force like that, and this is gonna give me my centripetal force. So I say this, which comes from Q V cross B, or rather the magnitude of it, is equal to the centripetal force, and the speed v naught squared over r. So I can solve this for r, the radius of curvature of the path. Doing that, I get, let me use lowercase r, that's what I've been using. Then solving for r is equal to, I think 1 factor of v cancels out. So it'll be r moved to the left hand side, everything else moved to the right hand side. It'll be m v naught, 1 factor having cancelled out, divided by qb. So that gives me the radius of curvature, and using that relationship I can say, but I'm solving for theta, I'm not solving for L. But I think I see why the question is telling me to use this. So I'm not given L, and unless I know this separation here, like L is an unknown quantity. But if I'm using small angle approximation, then this is what I can do. So without small angle approximation, this is the right triangle that I would have to consider, this right triangle here, and I would have to say the quantity that's given, with W, I would have to say W over L is equal to cosine theta. But for very small angle theta, cosine theta is approximately 1. So I can say the L that I'll need to use, I can say L is just equal to W, instead of L being W over cosine theta. So I can see, so from this point on, I can treat L as approximately equal to W, which is a given quantity, 5 centimeters. So I'll be using that at some point. Let me try to solve for theta here. So doing that, let me solve for sine theta first, or sine of theta over 2. Sine of theta over 2 is equal to L divided by 2r. I have expression for r. I'll just leave r here, and I'll just plug this in as I'm plugging in all the numbers. So with the small angle approximation, it simplifies my expression in 2 ways. One, I can say this is approximately equal to W over 2r instead of the unknown L. And the left hand side gets simpler. I can say this is approximately equal to theta over 2, where theta will be in radians. So I'll have to do that conversion at the end. So saying this is equal to that allows me to say, okay, I can solve for theta. Theta is equal to the rest of the stuff. So two cancel out. So with that, it's W over R. Oh, so simple. So let me plug in the numbers in Wolfram alpha. So W was 5 centimeter. So 5 centimeter divided by now the expression for R. That will be the proton mass. They didn't give me proton mass. I can just type in proton mass. Wolfram alpha, I'll look it up. Times the speed, 5.4 E6 meter per second. Oops, just meter per second. Divided by amount of charge. That will be elementary charge because it's proton. Times the magnetic field, 0.21 Tesla. So that should give me theta in radians. Now, Wolfram alpha doesn't know that I'm, working in radian units. So I'll have to say that times 180 over pi to do the conversion from radian into degrees. That doesn't look like a very small angle, but 10.21, maybe that's small enough. 10.1 degrees. I don't know how good that small angle approximation is, but I do remember as I was programming in this question, I tried to solve this without that approximation and it was too hard. That's why I said, use a small angle approximation. Because with the small angle approximation, it's doable. I think without it, in this expression here, you have L that's a kind of a function of theta, and I thought I was getting transcendental equation that's a little too hard to solve. But for the smaller angles, it's fine. I think the compared to the precise result, this is still like within 1%.